Okay, so our last speaker of the session is Amin Saberi from Stanford. He's going to talk about imagery.
Thank you.
Can we record and stream this talk?
Sure. All right. Thank you for having me here. Initially, I was planning to give a talk on the blackboard, but then when I arrived this morning, I realized that the room is not very well set up. I have only half an hour. I'm between you and your lunch. By the time I write the definitions, the time is up. So I decided to put a few slides together quickly. I hope it goes well. So the main application that I'm interested in is the traveling salesman problem. The problem is that we are trying to solve for an ambitious and frugal salesman is that we are given n cities, n points, and pairwise distances or the costs for traveling between every pair of vertices. I'm going to assume that the costs satisfy triangle inequality. So for every triples of cities I, j, and k, Cij is less than or equal to Cik plus Ckj. And the particular problem that I'm looking at is called the asymmetric traveling salesman problem. So the cost of going from I to j may be different from the cost of going from j to I. One of the problems that we are, the problem that we are interested in is to find a constant factor approximation algorithm for this problem. Meaning to find a polynomial time algorithm that for any instance of the problem finds a tour that is within a constant ratio of the optimum solution. This is central problem in algorithms. It has a lot of applications from logistics to DNA computing. It also shows up in a subroutine in a lot of problems in approximation algorithms. But it's also a very seductive problem. It's not because of its sort of the history or because it has such a simple and nice description. We have been looking at this problem maybe for the past 30, 40 years, and every time we feel like we are so close. When I was a first-year PhD student, my advisor gave this problem to me. I was like my first year, and said, I think we're gonna solve this within a, So I think we're getting there. And I'm gonna date myself. That was 15 years ago. Now, recently there is this new approach, new way of looking at the problem. That's along the lines of what Nikhil talked about, and I'm going to tell you about that. So this definition of thin trees is by Louis Godin. So it says, given a graph, we say a spanning tree is epsilon thin, if and only if for every cut of the graph, the fraction of the edges of the tree across the cut, the number of the edges of the tree across the cut is only an epsilon fraction of the total number of the edges. So if I want to draw this, so let's say you have the graph, you divide the vertices into two sets, S and S bar. For every subset S, you look at the total number of the edges of the graph, and then you look at how many of those edges belong to the tree. It shouldn't be more than an epsilon fraction. So, note the relationship with the cut sparsifiers that Nikhil talked about. So there he wanted for across every cut to be, within the same, sort of, the weighted version to be within the same, approximately the same amount. here, I want it to be only an epsilon fraction, and given that it's a spanning tree, I can put strictly bigger than 0. So it's like a one-sided sparsifier. And then, Louis Godin came up with this conjecture that there exists a constant c bigger than 0 such that every k edge connected graph has a c over k thin tree. So if you have a k edge connected graph across any cut, you have at least k edges, and no more than c over k of those edges belong to the spanning tree. Right, so you need the k edge connectivity, right? That, because you need at least k edges across the cut. So c is at least 1. Now, I'm saying this is a conjecture by Godin. He actually posed a weaker problem. The dependence on k wasn't linear, and he posed it as a problem, not as a conjecture. So if this turns out to be correct, he can take all the credit. If it turns out to be false, blame me. But I'm attributing it to him. It's a very interesting problem. The interest, and I invite you to, so as an exercise, try to prove this for a cube of dimension n. So there your graph is, let's say, of size n, dimension log n. Log n edge connected, you're looking for a tree that is c over log n 10. Now, why do we care about this particular conjecture? In his case, Godin, the problem was motivated by certain, embedding of graphs. Actually, the George's modular flow conjecture. So this is a problem in sort of orienting the edges of the graph so that across any cut, the number of edges in this direction, in each direction, is the same. But for why do I care? Turns out that an algorithmic proof for the thin tree conjecture gives a constant factor approximation algorithm for ATSB. So if you prove that conjecture, you can get a constant factor for the traveling salesman problem. Now, if you come up with a proof that's non-algorithmic, it doesn't give you the tour, but it still gives you a way of estimating the size of the tour. So an algorithmic proof gives you an approximation algorithm, and even a non-algorithmic proof gives you something that's of interest. The interesting thing about this connection is that the asymmetric traveling salesman problem is essentially a directed graph problem, right? Since the direction, in each direction, the distance is different, you can actually define it as you're given a directed graph and you're looking for a tour that visits every vertex at least once. And what this conjecture does, what this connection does, is that it turns the problem into an undirected graph problem. Now, this sort of relationship, discovering this relationship has been fruitful. Turns out that we cannot prove it for a constant c, but we can prove it for a constant that's for a function that's growing logarithmically with the size of the graph. So for O of log n over c equal to O of log n over log n, with Arash Asadpour, Michel Gomans, Alexander Modry, and Shayan Ovesqaran, we give an approximation algorithm with the same factor for ATSB. That was 2000. That's 6 years ago, and since then there hasn't been any improvement. Now, even 6 years ago, it was the first improvement after 20-some years. So, despite our attempts, we haven't been able to crack this The interesting thing about this algorithm is that it's using sampling. So essentially, it finds the spanning tree, the thinnest spanning tree, by sampling a random spanning tree from the graph. Now, it's not a uniform, it's not a tree that's sampled from the uniform distribution over the trees. In order to find the distribution, we have to solve a maximum entropy convex program. But essentially what it does is that it solves a linear programming relaxation. It samples a tree from that distribution. Yes, sir?
If you read about the symmetric traveling salesman problem, is there anything on?
Oh, yes. So for the symmetric version, there is a very beautiful, simple tree-half approximation algorithm for the problem. The conjecture is that it should be there should be a 4/3, so there is a gap there. That's again a longer-standing open problem. Now, if your underlying graph is planar, you can do it for a constant. 12 is the best constant I know. And that gives a constant factor approximation algorithm for the asymmetric traveling salesman problem. So let's say the distances come from the shortest path in a weighted directed planar graph. Let's say you want to solve the ATSP in a city that's planar, or it has a few bridges and tunnels. In that case, it will be a graph with bounded genus. Again, if it's constant, we can come up with a constant factor approximation algorithm. That's a result with Shayan over Skaran. So, these are the two things we have managed to obtain using this connection. Now, the thinness version that I defined for you is across all cuts. Given, Nikhil's excellent introduction, you can ask, what about the spectral version, right? Can we look at the, eigenvalues and eigenvectors, right? So you can come up with a similar definition. So we say a spanning tree is spectrally epsilon thin if and only if for every vector in Rn, X transpose, LT, and this is the Laplacian of the graph, is less than or equal to the epsilon X transpose Lg of X. Or, the way Nikhil wrote it, you can write LT is, positive semi-definite small G of X. Right? That's the equivalent way of writing. And Nikhil defined the Laplacian, right? So in this form, that's going to be useful for you. All right. Now, what's interesting about the spectral thinness, one is that it generalizes the combinatorial thinness, the thinness across cuts that I talked about. So instead of all vectors in Rn, if you restrict your attention to vectors that are 0 or 1, you will recover the original definition of thinness. And it can be also tested efficiently. So if I give you a tree and I ask you, is this a thin tree, combinatorially, we don't have a polynomial time algorithm. We don't have a way of testing it. But if you ask me spectrally, is this a thin tree, I can do that in polynomial time. So you can ask a similar question. If your graph is k-edge connected, does it have a C over K, a spectrally thin tree? It turns out that the spectral version of the conjecture, which will be the stronger form of the conjecture, is not correct. So the edge connectivity is not the right way of looking at it. You have to look at it a little bit differently. So G has a spectrally epsilon thin tree if and only if the effective resistance of every edge is at most epsilon. So the effective resistance, think about the graph as an electrical network where every edge has, resistance 1. You look at the effective resistance across all edges. This is exactly what, again, Nikhil talked about. So the vector way of looking at it is that if you look at the inverse of the pseudo-inverse of the Laplacian and you multiply the vectors corresponding to every edge, essentially moving the vectors to a space where they are, isotropic, no edge is too big, right? So the effective resistances are all small. In that case, you can find a tree that's spectrally epsilon thin. The proof that we know for this theorem use the proof of the Caddison-Singer problem by Nikhil and co-authors, a beautiful proof that they have came up with. But it's non-algorithmic. To be more precise, it doesn't give a polynomial time algorithm for finding such trees. It's using this sort of method of interlacing polynomials that we don't know how to make algorithmic. But using sort of this theorem and using this proof, this is a more recent result, beautiful result of Anari and Ovesgaran. They showed that every KH connected graph has O of poly log n over K in 3. So essentially, they turned the result of log n over log n to something that's, well, much smaller, sort of poly, so that's growing much slower. It's like log of n, but polylogarithmic in that. But because they use that proof, the result does not give the tour. It gives a bound on the integrality gap of the linear programming relaxation. Or another way of looking at it is that if I give you the instance of the traveling salesman problem, their algorithm can give you the size of the tour within the ratio of poly log n, but it cannot give you the actual tour. All right, so this turned out to be faster than I thought. So to summarize, the conjecture that I'm interested in is the thin tree conjecture. Given the sort of the k-edge connected graph, you're looking for an O of 1 over K thin 3. That's the Godin's conjecture that we don't know how to prove. We can come up with a spectral equivalent spectral version that we can prove. So if the effective resistance is less than or equal to 1 over K, we can find an O of 1 over K spectrally thin 3. Our proof for it is non-algorithmic. And if you want to sort of establish the relationship between these two problems, if you no, I'm sorry, the arrows should go in the opposite direction. So if you have this, if the effective resistances are small, you know that you have KH connectivity. And if you have a spectrally thin 3, you can actually, you know that these are also thin 3. So they go in the, so the proof of this conjecture does not yield the proof of that, but the result of, Ovesgaran and Anari, sort of created the connection, but losing a factor of this poly log n. So essentially, it grows with the size of the graph. The obvious another way to look at it is that, this is the L2 version of the conjecture that we can prove using, characteristic polynomials, the method of interlacing polynomials. This is the L1 version, the combinatorial version that we don't know how to prove. Proof of that conjecture will be absolutely interesting. Making the proof of this, algorithmic again, a very interesting open problem. Even for the first version on special classes of graphs, for example, graphs that have bounded tree width could be quite interesting. So with these 3 open problems, I'll conclude. All right, very good. Thank you.